Good afternoon, everybody. Thanks for joining today's meeting at CCAV Center. Today's talk is on driving autonomous vehicles in partial observable environments. Today's speaker is Dr. Abdullah Redwan Nawaz. Dr. Nawaz is a postdoc at Access Laboratory. Before joining the North Carolina State University, he was doing a postdoc at Rice University and Nagoya University in Japan since 2018, 2020, and 2017, 2018. He received his PhD and master degrees in information science from Japan Advanced Institute of Science and Technology in Japan in 2017 and 2014. He received his Bachelor of Science degree in Mechanical Engineering from Rajshahi University of Engineering and Technology in 2011 in Bangladesh. His research interests include robotics, artificial intelligence, autonomous systems, reinforcement learning, deep learning, computer vision, behavior planning, optimal control, formal methods, and model checking. With that, Dr. Nawaz, the stage is yours. Let me stop sharing.
Thank you so much for having me. Thank you so much, everybody, for joining. About a year and a half ago, I talked about anomaly detection for autonomous car in the very amazing seminar, and it feels so good to be back. And today I'll be talking about driving autonomous vehicle in partially observable environments. So this talk will try to bridge the gap between the theoretical development and the real-world application for autonomous vehicles. So when we talk about autonomous vehicles, these are the robots. And in many situations, autonomous vehicles are better suited than humans because they are precise, they're intelligent, and they don't get bored like humans are. And since the beginning of the 20th century, we are the roboticists are trying to build a system that can operate fully autonomously without any human intervention. And as we firmly believe, soon autonomous cars will be commercially available at large scale, and the question arises if we could trust their planning behavior. Now, with the current state of the practice, autonomous cars have been primarily tested in the control environments, and further efforts is needed to transition this autonomous technology from innovation space to the real scale adaptation of autonomous vehicles. So again, the autonomous vehicles doesn't mean not necessarily a self-driving car. So it has many applications from the precision agriculture, self-driving car to disaster response. Autonomous vehicles are everywhere.
So we have a comment in chat box. Some have problem to hear you. If you can talk louder or get closer to your computer.
Okay. Is it better now?
Of course, yeah.
Okay, all right. Thank you. So there are basically two pieces of this talk. And first, I'll be beginning with the planning under uncertainty problem for autonomous vehicles and how we can mathematically model them. Then I'll be talking about several state-of-the-art solution algorithms to address big state space problem, long planning horizon, and uncertainty problems. Finally, I'll conclude with some inspiring ideas on our ongoing work. So broadly speaking, motion planning for autonomous vehicles can be thought of as a given a vehicle with finite degree of freedom. We need to find a trajectory through its configuration space. And canonically, a motion planner is implemented with four primary building blocks from state estimation, planning, control, and perception. So classical motion planning algorithms consider a perfect knowledge over all the elements of the environment and then can just compute the solution before actually executing an action in the environment. So in reality, the uncertainty is an unavoidable part of each building block. And that's why there's an urgent need for developing a motion planning algorithm that can assure the safety of a motion, particularly in the presence of uncertainties. So as I mentioned earlier, most of the motion planning algorithm ignores uncertainty associated with each building blocks. The crux of the challenge involves making decisions under uncertainty, and that is choosing an action based on often imperfect observation and incomplete knowledge of the world. And to begin with the motion planning algorithm, we need to first categorize the sources of uncertainty. So we actually categorize the sources of uncertainty in three categories. One is motion uncertainty from the noise that affect the system dynamics. We also have sensing uncertainty, that mostly comes from the noisy sensor measurement and which also refer to the imperfect state estimation. And besides, we also have environmental uncertainties. That includes the uncertain static obstacles, pedestrian dynamic obstacles, and so on. So on the right-hand side in this figure, you can see there is amazing view from the autonomous car through its sensor. And for sure, this view lacks the detailed information that we humans perceive on our day-to-day driving. Furthermore, a perfect controller does not exist. So there are some source of uncertainty we need to address if we want to replace a human driver with an AI agent. So to summarize, so in classical planning, we assume that all the elements of the environments are known, and we then just compute the solution before ever actually executing an action in the environment. So, but the problem is, what if the agent doesn't know all the elements of the environment? And that precludes it from being able to plan a solution beforehand. And this is where the reinforcement learning comes in, which enables us to consider the known part of the system and gradually know the unknown part via search and trials and error and reward-based interaction. So there are basically two types of reinforcement learning, and we can categorize them by asking a simple questions. And the question is, can the agent make a prediction about what the next state and reward will be before it takes each action? If the answer is yes, we call them as a model-based reinforcement learning, otherwise it's model-free reinforcement learning. So in reinforcement learning is aimed at finding the sequence of action that an agent should take to maximize a long-term reward. And this sequential decision making usually modeled as Markov decision process, where at each time the agent chooses an action based on a policy with the aim of maximizing its value. So here on the right-hand side, you can see a reinforcement learning setup. In this setup, our car is an RL agent, which can take some actions, and we can observe the outcome of the actions from the environment. So basically, the environment tells us which state the car will be and what kind of reward it will get for a particular actions. And since the environment reveals to the robot or car only by interactions, we cannot just compute the solution before ever actually learning the action. And therefore, we must need to have a policy for taking an action based on agent's current state. So we can think of a policy as a function that relates the agent's state to its action. But how to evaluate a policy and how to tell a policy is a good or bad? And to do that, we need some sort of value function. So let's talk about mathematically. So mathematically, MDP is a four-tuple. We have a set of states, we have a set of action A, we have a probability transition P, and we have a set of rewards, scalar rewards. And let's start with a very simple animation. So basically, there is a robot should be here. So robot can take an actions to move to the right or move to the left. So depending on each action, the environment will decide which state the robot will be. So the questions that we want to answer, how to find a policy for the car to get from the starting locations, which is these locations, to the goal location. And you have to remember that we also want to avoid these black states, which are obstacles, and X is red zone, that's danger zones. So there's one solution that may look like this, and given that turning is always difficult and costly operation, so we may want to minimize the turning, and assuming that the agent actually reach to its next state based on the action forward and left. Those are two kind of actions that agent takes to reach the goal location. So since the MDP states and our actions are discrete and the agent fully knows its environment, we can find a deterministic optimal policy through a dynamic programming approach. However, the difference between a plan and policy is that if something went wrong in between, then the car can dynamically replan its trajectory based on its policy, where if you have a plan and if something goes wrong in between, you are completely stuck. So if this plan doesn't work, so basically the whole mission fails. But if the agent has some problem in between, the agent can find another route to the goal location. So moving on, then MDP-based planning, we capture uncertainty in decision making, so in the form of transition probability. However, a practical difficulties arises in MDP-based planner because of the strong assumption of observable states. So meaning that MDP does not capture sensing uncertainty. And for instance, in the AV pedestrian detection module are noisy and frequently produce a lot of false positives and false negatives. And such kind of sensing noise give rise to the drift to the state estimation and makes the system partially observable. So when the agent only has the partial observation of its environment, or when the observation is imperfect or stochastic, we can frame this problem as a partially observable Markov decision process, also known as a POMDP. So mathematically speaking, POMDP is 6-tuple. So in addition to the MDP, so POMDP consider observation space and the observation probability. So now the same problem can be reframed as how do you find a policy from the start location to the goal location for the car while you have to address the sensing and motion uncertainty. So to summarize this sensing uncertainty, we can assume that there are some landmarks that robot needs to see in order to localize itself. So if robot cannot see the landmarks, the sensing uncertainty will be huge. So, and the robot may be in completely different states. At the same time, and we have some imperfect controller that give some drift in the control. So the solution may look totally different than MDP problem. So the explanation is very simple. So robot will turn from here because it wants to see the landmark to reduce the localization uncertainty or state estimation uncertainty. And then it will follow a different route to reach to the goal locations. So in the POMDP agent can perform action which affect the systems with the goal to maximize a reward that depends on the sequence of the state, observation, and agent's action. However, the agents cannot directly observe the system state, but at each discrete point of the time, the agent makes observation that depends on the state. So the state is partially observable. The problem is the POMDPs are notoriously difficult to solve when the number of the states and observation are even moderately large. So that's why we have the notion called Belief-MDP. And a Markovian belief states allows a POMDP to be formulated as a Markovian decision process where every belief is a state. So in Belief-MDP, the agent uses POMDP's observation to form a belief in what the system currently is. Now the belief is called a belief state and is expressed as a probability distribution over all possible states. So now you have to maintain a probability function that your agent could be anywhere in the grid with some probability. And POMDP can be treated as a fully observable system in the belief space. The solution of the POMDP is a policy again, but this time we'll be mapping an action from a belief state, not a normal state from the robot. So in Belief-MDP, agent state are replaced by the agent's belief again. So, and at each time, so basically agent's belief can be updated through a Bayesian inference to account for the observation. In the belief space, the problem becomes again fully observable, and we can solve the Belief-MDP using some sort of dynamic programming again. The main difficulty is that the dimension of the belief space much larger than the state space. So the dynamic programming will not work at this time. So for instance, in the discrete case, the belief state is a continuous but finite dimensional. And belief update can be carried out exactly with the expense of huge computation, even though you're considering the discrete space. On the other hand, in the continuous space, the belief space is infinite dimensional. So we need to have some sort of approximation method to approximate our belief space. So here is a high-level overview of a POMDP-based planner. So to compute the car current state xt, we need to reason about the car current control ut and sensor reading zt at corresponding time t. And since the current state xt is affected by sensor noise rt and motion noise qt, we need to maintain a belief space bt over all possible states of cars. Thus, our motion planner generates a policy pi based on the current belief space bt from the state estimator tau. Again, the main challenge we have to address is belief space is much larger than the state space. So the optimal behavior in POMDP domain is expected to strike a balance between exploring the partial observable world and acting in a goal-directed manner. Ideally, we can synthesize an exact policy of POMDPs by enumerating all possible belief space in the belief domain if we have infinite computational power. However, POMDPs are notoriously difficult to solve when the number of states is even moderately large because the solution algorithm efficiency decays exponentially with the size of the state space. For example, in the finite horizon problem, we have a complexity P space complete. On the other hand, if we have infinite horizon planning problem, POMDP is undecidable. So therefore, it is unrealistic to, in a larger scale POMDPs, to seek a globally optimal solution in exact belief space due to the curves of dimensionality and curves of history. And plus, sometimes it is impossible to enumerate over all possible outcomes for computing a valid policy or optimal policy. So there are several POMDP solution algorithms have been developed and that use approximate value iterations based on point-based updates. One thing that we have learned from the literature is that the value function of a POMDP is piecewise linear and convex as a function of a belief space. So basically, point-based methods do a combination of sampling to find an important part of the belief space and a dynamic programming updates on value function. So utilizing this method, we can then compute a valid policy over a goal constant belief space. So the idea is we have a small belief space, which is a subset of the actual belief space. And we name this belief space as a goal constant belief space. The goal constant belief space only contains belief visited by discrete execution achieving the high level objective and is generally much smaller than original belief space. So now that we have a goal constant belief space, we may use an offline synthesis method that can compute an optimal policy before execution. The upside of this approach is that the execution is extremely fast when you have a desired policy and we synthesize this policy offline. So nonetheless, the downside of this approach is that a lot of computation might unnecessarily be done during synthesis, resulting in difficult to scale. And another approach that is very interesting and promising is online planning that interleaves planning and execution together. So online planning has proven to scale very efficiently, relying on the fact that performing many fast approximate updates often results in more useful value function than performing a very few exact updates. Online planning works well when you have replanning is likely to be succeed, but it often fails when replanning is difficult or sometimes infeasible, so making it hard to ensure correctness. So now we are facing the problem of correctness. So bringing this technology to real-world applications, we will be facing some guarantee problem. And as I mentioned before, there is a correctness problem. And for example, in this slide, we can see the navigation of the robot in indoor environment. Let's say an office environment, and traditionally, POMDPs are formulated with optimality objectives that we have reward function and we want to maximize this reward function. However, for the robotic domain, correctness guarantee of an accomplished task is natural requirement. So in this work, we study POMDP with a common Boolean objective called Safe-Reachability, which requires that with a probability above a threshold, the robot eventually reaches a goal location while keeping the probability of visiting unsafe states below a different threshold. So the key idea is to represent the POMDP with the Boolean objectives using a symbolic constraint. We employ a SMT solver, which stands for Satisfiability Module Theories, to efficiently search our solution space. So mathematically, we can formulate this POMDP with a qualitative objective. The qualitative objective is safe-reachability. So in our setup, we are given a POMDP as an environment. We have initial belief as a robot initial position. We have replanning probability bound, safe-reachability objective, horizon over planning, and our goal is to synthesize a valid k-state partial conditional plan or policy subject to replanning probability bound. Now the problem is, if you want to synthesize a full conditional plan or policy that consider the solid line and the dotted line, the computation would be huge. So the one idea that we want to use to improve the computational efficiency, that partial conditional plan. So the partial conditional plan that covers only a sample subset of all possible events and approximate a full conditional plan. So our approach, construct and partial conditional plan, parameterized by replanning probability. The idea is, in online planning, you cannot predict every situation. So when you have replanning probability higher in that particular state, then you may need to do replan online rather than offline. But the rest of the partial conditional plan, you may synthesize offline. So for synthesizing a valid conditional plan, so we begin with generating an arbitrary partial conditional plan first and ask the symbolic model checker whether this plan satisfies our safe-reachability requirements or not. So if the plan does not satisfy the requirement, the symbolic model checker provides us a counterexample which we represent as a constraint, and we store this constraint and we learn from this constraint as we progress for synthesizing a valid conditional plan. So to further improve the computational efficiency, we cache partial conditional plans for sample belief states and reuse this partial conditional plan if possible. So here is a quick demonstration how this partial conditional plan can be executed. So this works is a joint work between my colleagues at Rice University and myself. And in this video, you can see a fetch robot, which has 7 degrees of freedom arm and a head-mounted camera, and it has a base, differential wheels to navigate. For this robot, the robot doesn't know these cabinets, which are uncertain to the robot. So initially, the robot has a plan that reaches from these locations to the corner locations, which is partially observable as of this moment. And then when the robot sees these obstacles, and then the policy starts to branch out. So this comes from the online planning. So when you have no feasible plan, then you can replan based on your current state. So when the robot reaches to the particular state, see there's no valid plan, then the robot replan for that particular state, and robot navigate to the goal location successfully without hitting any obstacles. So our safe reachability requirements is satisfied. So now we talk about the point-based value iteration. So we can actually construct a small belief space and do dynamic programming, and still it works well for a small scale POMDPs. And when we want to scale this problem for large scale POMDPs, and it still doesn't scale well because the dynamic programming is very expensive and doesn't scale well for the large scale POMDP. So an enabling idea behind a scalable domain-independent POMDP algorithms have been the notion of Monte-Carlo sampling. A particular successful algorithm, often known as a POMDP algorithm, proposed by David Silver in 2010, searches for an optimal policy by a particle filter and Monte-Carlo tree search. Silver used the particle filter to approximate the belief space and Monte-Carlo tree search for efficiently synthesize an optimal policy. Later in 2013, the team of David Hutsu's group from National University of Singapore proposed an improved algorithm called DESPOT that reduced the variance of the Monte-Carlo tree search with theoretical guarantees. Hutsu used a lower and upper bounds over Monte-Carlo tree search to reduce the variance. In 2019, our group at Rice University, we're focusing on the POMDP, sampling-based POMDP planning with safe-reachability guarantee. So in autonomous robots operating in uncertain domains often face tasks with the Boolean objective requirements, such as reaching to a goal location safely, and optimality criteria, such as reaching to the goal location as fast as possible. So this problem can be modeled as POMDP with quantitative and qualitative objectives. So in this study, we present a new policy synthesis algorithm called POSMC, which stands for Policy Synthesis with Statistical Model Checking. So our approach, actually, previous approach used symbolic model checker, which is SMT solver, and we replaced the symbolic model checker with the statistical model checker to ensure that qualitative requirements are satisfied with high confidence, and we can actually use sampling-based approach to guarantee those probability. So in POMDP world, reachability, safety, scalability are orthogonal properties. Several works have focused on satisfying only one kind of property. However, in our work, we try to satisfy all the properties. So our work lies in this domain. So our proposed algorithm, POSMC, is based on Monte-Carlo tree search and construct a valid policy for POMDP under quantitative and qualitative objectives. To begin with, we are given a black box simulator from where we can actually sample the robot current state and reward. The algorithm actually constructs a search history by simulating the state transition and observation from the black box simulator. So given the robot's current belief state, POSMC uses a generated search tree to estimate the reward of a candidate action as well as the probability of success. So when you do simulation here, so we not only compute how the action will give the maximum average reward, but also consider what is the probability that this action will satisfy the property or requirements. So let's see the demonstration. So in this video, you can see these yellow cylinders are unknown obstacles for the robot. We significantly increase the number of obstacles and robot has a larger grid to explore. So as the robot reaches close to the obstacles, gather more information from the head-mounted 3D camera, and then robot has more confidence over these obstacles and change its behavior based on the synthesized policy. So as the robot reached to here, robot was not very sure there is an obstacle, gather more informations, and then robot are confident and the obstacles become red, that means robot are fully confident, and then robot averts this position. And finally, robot reached to these locations to pick the can. So we benchmark our algorithm with our previous algorithms, and we can see the previous point-based approach does not scale well for large scale POMDP. So especially we have 13 times 3 grid is the limit for the previous approach, but when you use the sampling-based Monte-Carlo tree search, we can scale this problem in larger POMDP with 14 times 4 with 7 states in total of 1 billion belief states. So we have a belief space which exact domain is 1 billion, but since we are using sampling-based technique, all you need to care about is 10,000 sample, and 10,000 sample is good enough to approximate 1 billion belief space with 95% confidence. So there's a huge improvement in sampling-based approach. So now we talk about sampling-based approach and reinforcement learning. And a big issue in the reinforcement learning is sometimes we cannot actually afford to make a lot of mistakes. Like we are only depends on interaction-based learning, and interaction-based learning is not very suitable for safety-critical domain. So there's two levers that we can see in machine learning are one, we can learn from interactions, our machine learn from interacting the environment. And the second, if we cannot learn from the interaction, then what we do? We actually record our past interaction and we call them data. So it's the combinations of learning and interaction that makes us learn fast. It's not only the interactions. So in this framework, I'll be talking about data-driven reinforcement learning approach, a framework that combines the data-driven learning and interaction learning in one framework. So one of our work where we use the data-driven reinforcement learning is for feedback plan synthesis for long-range autonomous underwater vehicles. Now, ocean ecosystems have special temporal variability. That means the ocean current changes based on the space and time. And dynamic, and it's very dynamic and complexity, and it requires a long-term deployment of an autonomous underwater vehicles for data collections. So the ocean environment has force and momentum for changing water currents, which are generally on the order of magnitude of the operational vehicle velocity. Therefore, it's not straightforward to generate a simple trajectory from initial location to the goal location in such an uncertain ocean environment, as the vehicle can actually significantly deviate from the prescribed trajectory because of the external disturbance that we have from the ocean current. So in this work, we actually are focusing on how we actually plan for under such kind of external ocean currents. And even though this work study ocean environments, similar problem arises in autonomous driving. For instance, when the car is running on the low battery condition, in state estimation remain challenging, feedback planning must consider state uncertainty that we can actually frame into a stochastic energy-aware path planning problem. So normally, when we talk about the solution of the POMDP, we are trying to solve a stochastic shortest path problem. But in many situations, a stochastic shortest path is not desirable. For example, in the ocean environment, so we want a path that is stochastic energy efficient. So in this work, so we are trying to solve a POMDP problem in oceanic environment. So where our ocean environment is given as a POMDP, and then the agent has a set of actions, that discrete actions that agent can take, and our target is to reach to a goal locations, which is BG, and while minimizing the energy cost. So here is a quick demonstration of our algorithm. So the Monte-Carlo tree search that I discussed earlier, so that Monte-Carlo tree search is also can be applied in here to solve the same problem. But in this case, we actually modified the Monte-Carlo tree search so that we can consider the energy awareness from the flow field. So we have this flow field data, it's called ROMS data, which is available. And then during the simulation steps, we can actually simulate each action outcome in terms of the reward and energy cost. And then we can actually average this reward and energy cost to choose an optimal action based on the current robot states. So if you can see a quick video here. So you can see the robot actually need to go to these locations, but there is an ocean currents that directed in these locations. So normally the POMDP planner will take a path that is not energy efficient, and maybe the shortest path would be like this. But in this particular video, you see the robot is deviating from the shortest path, taking the energy as a favor for the planning and reach to the goal locations. So it goes along the ocean currents and to reach to the goal locations. So, and this is possible if you consider the constraint. So now, in many situations, it's not straightforward to formulate the objective with reward maximization alone. And for example, the AUV under search and rescue mission, the main goal would be finding as much as target as possible while avoiding threats and that may endanger the missions. Meaning that if you have an obstacle, so the earlier informant, there is no obstacles. If you have an obstacles, then the problem becomes significantly complex, and we can think about some constrained POMDP problem. And this constraint POMDP is an appealing framework for dealing with this kind of multi-objective sequential decision-making problem when the environment is partially observable, right? And we have also some constraint about the hitting obstacles or energy constraint. So this model assumes that the action incurs not only reward, but also different type of cost. And the goal is to finding an optimal policy that maximizes the expected cumulative rewards while bounding each expected cumulative cost below a certain threshold value. So to give you a glimpse of the problem, so we have this notion called belief space, which can be represented as a triangle. And you can see the belief space is quite a big state, and finding a policy under this belief states is easier compared to the reachable belief space, which is a subset of this belief space. So your sampling algorithm needs to be very efficient to find a policy that lies under this area. And then if you have safety constraint on top of the reachability constraint, then you have to have a very efficient sampling algorithm that finds the solutions within this very constrained belief space. So in this work, we are actually focusing on the marine environment. So we consider the obstacle avoidance, energy, cost, and everything together in one big framework. And for long-term autonomy, for an autonomous vehicles, so we need this sophisticated but reliable planning and navigating to achieve this guaranteed performance lasting days, weeks under uncertainty while dealing with resource constraints. So we address these issues by adopting the motion sensing and environmental uncertainty via POMDP framework, and we propose a method with a novel extension of POMDPs, incorporate spatial temporal varying ocean currents as an energy, dynamic obstacles as a cost, and the distance as a reward. So existing POMDP solutions, such as cost constant POMDP, only consider the cost to the hitting and the obstacles, do not consider the energy factors. So, but in our framework, we present a scalable energy cost constraint POMDP algorithm utilizing the predicted ocean dynamics, and that optimizes energy and environment cost along with the goal-driven reward. So it's been a complex framework and that consider many different constraints. So we have this energy cost constraint POMDP, and we have three primary factors in action selections. The first one is the expected total discounted reward, the expected total cost, and the last is expected total energy consumption. For example, in marine environment, if the distance between the vehicle and the goal location is a useful factor because the vehicle gets a higher discounted reward as it approaches to the goal location. So the distance between the vehicles and the nearest obstacle is another useful factor. As opposed to reward, the vehicle gets higher cost when its probability of hitting obstacle is higher. Finally, the vehicle's endurance improvement utilizing the ocean currents is another important factor, since going against the flow requires more energy consumption than usual. So thus, the derivation of our algorithm starts from optimizing the value function by looking for a policy taking the current belief space. So we rely on predicting ocean dynamics for given time, depth, geographical locations to sample efficiently in marine environments. Earlier, we have this ROMS data that provides a sparse forecast over the ocean data, but our motion planner is continuous. So we need to actually have some sort of prediction algorithm that actually give us a continuous domain prediction for the ocean currents. So we efficiently planning, if you want to do efficient planning, so the continuous prediction and action evaluations are very important. And therefore, we train a deep neural network to estimate the ocean dynamics based on the ocean data, which is ROMS data that we had earlier, and use this model for evaluating the future cost of an action. We frame learning in ocean dynamics as a multivariate time series prediction in a continuous domain and designing a recurrent neural network to handle a sequence depends among the input variable. So here is a quick glimpse of the prediction of the ocean currents. On the left-hand side, you can see the ground truth. On the right-hand side, you can see the predicted ocean currents. We never seen this model before, so we got based on the data, we can actually predict the ocean currents, and which is very close to the actual prediction. And the difference between this one and this one is this one is in continuous domain, and where this one is a discrete domain with a resolution of 1 kilometer by 1 kilometer grid. So this one is much better for continuous action prediction. So again, this proposed solution algorithm also Monte-Carlo tree search with the policy iteration approach. So a little bit different algorithm that we use in this scenario. So first off, we have this constraint problem that we actually have a primal objective functions. So meaning that our objective is not only satisfy the maximizing the reward function, but also satisfy the constraints. And then we are approaching this problem by converting into dual problem by making this constraint problem to an unconstrained problem using some Lagrange technique. And then we synthesize the optimal policy on unconstrained problem using the Monte-Carlo tree search. So the quick video is like this. If you compare from previous approach to this approach, so in this case, there is an obstacles, dynamic obstacles in the environment, and robot has no idea about the dynamic obstacles, and robot can sense the obstacles when it is close to its sensing boundary. So robot actually sampling the world and getting the information where the obstacles are, and also utilizing the ocean current to reach to the goal location. So we also actually deploy our robot in real-world ocean environments, and we compare our ECC POMDP algorithm with the baseline CC POMDP algorithm in terms of the trajectory length, average velocity, and the mission completion time for different kind of water layers in the absence of obstacles, within the presence of obstacles. So in contrast to the existing CC POMDP, which only consider cost constraint, our approach, actually, our AUV navigates with higher velocity while following the ECC POMDP policy. Here you can see the trajectory is longer, but the overall mission completion time is faster because this is the simple effect that going against the water currents requires more energy and more time to reach to the goal location. So you will be sacrificing your linear velocity and you will have more angular velocity, which is costly. So our real world experiments is conducted off the coast of North Beach, Miami, Florida, in the region surrounded by mangrove with a shallow water and clear water. Here you can see some blue dotted. So these blue dotted represent the virtual obstacles that robot has no idea about their position and can only be detected when they are in the close proximity. And the robot reaches to its goal locations while avoiding all these obstacles, considering the ocean current, water current, and everything together, and reaches to the goal locations, which is right here in this area. So I'm almost finishing my idea of the partial observable environment, but as it is well understood that AUVs inherently requires a great deal of autonomy, and since there is literally no human being behind the wheel, and the stakes are high. So we argue that AUV decision making must conform to human-like logical explanation in the real time based on the current situation and the potential evolution of all the relevant actors in the scene, including itself for some times into the future. So there are some urgent needs for AUV development. So we want to developing decision-making algorithm for AUVs need to be think of under uncertainty. Another important factor is that we need to utilize the logical expression to provide a useful abstraction of the belief space. Last but not least, we also want to have human interpretable policy that are amendable for the guaranteeing properties such as safety, reliability, and so on. So all we are trying to do we want to make the robot more humanized? So our AI agent needs to be more humanized. And if you want to make the AI agent more humanized, so you need to understand or interpret this policy. As of today, most of the deep learning based policy are kind of black box to us, and we cannot interpret this big deep learning policy, and that is the main safety concern. So recently, our group has focused on generating a safe behavior tree coordinator to guide an autonomous vehicle to satisfy the goal of mission without violating the mission safety requirements. The good thing about the BT synthesis is a semi-formal approach to structure the switching between different actions of the AP. Unlike the popular deep reinforcement learning algorithm, which policy are basically from neural network, BTs are human readable, interpretable, and adhere to a coherent and compact structure. So besides, BTs have the benefit of being more easily interpreted than conventional policy and being amenable for the verification purposes. So since we can interpret a policy, we can also verify this policy using the existing model checking approach. So that's pretty much my talk. Thank you very much for having me today. And if you have any questions, I will be happy to answer. Thank you very much.